Hello everyone. Today is we're talking about what's it called? Right, first derivative and second derivative tests. Sorry, it's a bit early and I am still mildly tired readjusting after spring break. But let's say we have f of x equals x squared. That's been like my example for everything. So x squared, we know what that graph looks like, which is why I chose it. It's like that, and then arrows to imply that it goes on forever. And then we know through the power rule, we can quickly deduce that the first derivative is that, and then if we take a derivative again, we get what is called the second derivative, which I just realized is the first time I'm mentioning this. So taking a derivative of this, we get 2. And that is the second derivative, so f double prime, also shown as like d2y over dx2 or something like that. That's like another way it's shown. There's other ways to notate it, but those are the two common ones. So there are different things that we can tell off of this, and I'll start talking with the second derivative because that's the one that is easiest to show. So there is a thing in all functions that are, I guess, aren't like linear. All functions that aren't linear. I should use the line tool for this. Shift. And then we'll do that shift. And then we'll say that this function comes in, right? That's how it works. So as we can see, there are parts. The described concavity is basically if I were to pour water, like just like yeah, it's blue. If I were to pour water onto this so it goes down, the water here would just go downwards, right? It would just slip off of it. But if I were to pour water here, it would create like a little pool thing. So if the water stays in a little pool like this, that's what we call concave up. That I'm still getting used to not writing in cursive for these videos. And then if it were to, go down like this, it would be called concave down. So off of our graph of x squared, if I were to draw that out very quickly, pencil down, move it back to red. If we were to pour water in this, as we can see, it would just create a little pool. Sorry. Excuse me. It would create a little pool, meaning that this is concave up, and that's shown in the fact that the second derivative is positive for everything, meaning that this entire function of x squared specifically is concave up. That's what I mean by that's usually the easiest to find. Now, I would say we'll go back a little. Actually, we'll just do it now since we're talking about concavity anyways. X squared is a pretty simple one. If I were to do x cubed, alright, what is... Okay, well, we're just gonna pretend that it's just some random trinomial. So I'm gonna put x cubed dot dot dot. And it's like, I should make this colored, and then, it's like that. It's like that. We have multiple like we have this area over here. If I were to pour water, it would be concave down. That's a darker blue. But if I were to pour water here, it would create a pool. So when does it swap exactly? And there is a way to find exactly when it swaps, and it's through finding the second derivative. I don't know what this function is, because I actually didn't do that much with trinomials in school. But there would be a point where, to be honest, okay, let me see what I can approximate as this function so I can write out even like an example. So I'm gonna, okay, I just played around with trinomials in Desmos, and let's say that this is, this function is like, let me, spacebar, nope, whatever that did, I think. Okay, that didn't do anything, I think. But if I were to say that this function is x cubed minus 4x, right, that's a pretty normal trinomial function. Its derivative would be 3x squared minus 4, and then its second derivative would be 6x. And the way to find where this original function f of x changes from concave down to concave up is by looking at the second derivative. So if I were to graph the second derivative, I'm going to make it this pink color. I don't actually like pink, but yeah, and then we're going to quickly notate stuff because now we know what this function is. So that's 2, that's negative 2, 2, 3, 4, 5, 6, meaning that was 2, 3. So let's say something like that. Okay. We have a line like that. It's super not straight. Use rulers, guys. And it's like that. Where the second derivative graph hits 0 or is undefined is where the concavity swaps. Usually. It's where you look to see if the concavity swapped. Sometimes you'll have cases where it will be there, but it won't, like, do much. It'll stay concave down. And those points where, so yeah, here we know that f double prime equals 0 when x equals 0. So f double prime of 0 equals 0. Now if we plug 0 back into this function, f of 0 also equals 0. So the point of inflection, I'm going to erase this because it's just like very getting in the way. This point, which I'm going to mark with the same second derivative color, is the point of inflection. So, point of inflection, POI. Point of interest. So, that's concavity. See where it swaps. And the the first derivative test is very similar. Now that I explained how to find points of inflection, we're finding a different thing, though. It shows a different thing. It shows minimums and maximums, or what are called extremas on the graph. So let's say that, this is, whoops, I'm still in colored mode. This is 3, this is 3, And our domain that we actually care about is -3 to 3 of x, I guess, or of f of x. I don't know how to write that out. So what we're looking for is where this equals 0. Meaning that we'll have to find where 0 equals 3x squared minus 4 divided by 3 square root equals x. So, and then because this is a square root, this could be plus or minus. It could be plus or minus, right? Or no, x doesn't equal plus or minus, but this is equal to, yeah. So, at negative square root of 4, 3, I guess, which is 2 over square root of 3, right? That would be this point right here, which I'm going to color as, what's a nice color we haven't used yet? Purple. Yeah. So yeah, this purple dot here, this purple dot here, that's where it maxes out, or where it's extreme, called extrema. So if we were to draw this thing, it would be like down here because it's a derivative or a quadratic. What the fuck? Okay, it's quadratic. And if we were to go into color mode, right, like around here-ish, around here-ish, is where it'll hit 0. Same thing, look for where it's 0 or undefined, and then those are the points where it's an extrema, but you don't know whether or not it's a minimum or maximum just by looking at where it equals 0. To figure out whether or not it's a maximum, like if I were to look at this one right here, we would see on the first derivative that it goes from positive to negative. So, if we were to think about what our first derivative graph is doing, it's something like that. Goes from positive as it goes up, and then it hits the extrema point where, because of how tangent lines work, that's like, because of how tangent lines work, that's 0 at that peak. So it hits 0, and then it goes to negative. That's how we know it's specifically a maximum. And then the opposite thing can be said for minimums. Whoops. Where it'll go from negative, hit 0, and then go to positive. So, and then the other big thing I want to talk about, kind of relates to this, is that you'll get questions, a lot of questions, where it's like, okay, well, you are given I think you have to justify why you think that an extreme is here. Whenever you justify something, always say, be very specific. Don't like say, if you're referring to f of x, say f of x. If you're referring to the first derivative, say f prime of x or dy dx. If you're referring to the second derivative, say it. Don't generalize and say it, because they're gonna pretend to be a dumbass and not know what you're talking about. And then also, uh, just say like, oh, if I were to say, How do you know how do you know x squared only has one max or one extrema? How do you know if it's like a minimum? So I would say x squared has x squared, I should say d dx of x squared equals to x, where it can only hit or be 0 equal equals 0 or be undefined at x equals 0. So, and let's say the limit, or no, as x approaches 0 from the right, or from the left, f prime of x is negative, right? You can write that to show that's negative. And as x approaches 0 from the right, f prime of x is positive. That's like an answer I would realistically write. Or that's like the justification. And that would be like the answer for that question. And now I have to record a video on forces. Anyways.